Hi folks, welcome to the Chapter 4 Concept Roundup for Math 621B. This chapter focuses really on trig equations and trig values and unit circle and things that are related to trig values. If you check the video description below, you'll find a link to downloadable notes, to a review, and you'll also find that the different topics that are covered here are kind of time-stamped below there. So if there's something you're interested in, you can skip straight to it. So here are the big ideas we're going to look at, and let's dive right in. Angles in standard position are pretty straightforward. They're measured counterclockwise from the positive x-axis. So if we wanted to sketch 70 degrees, all I do is I go to the positive x-axis and go counterclockwise 70 degrees. That's what that angle looks like in standard position. If I wanted to do 450 degrees, well, I just keep going counterclockwise. So here's 90, 180, 270, 360, and another 90 would get me to 450 degrees. So you can see that our angles, they can go beyond a full revolution. Negative 120. A negative angle means that we move clockwise instead of counterclockwise. So I'll start at the same place, and I'll go 90, and then another 30. That's the angle of negative 120 degrees in standard position. One thing that's worth mentioning here is there's also this little angle that's created with the x-axis. That smallest angle that you create with the x-axis, whether it's on the positive or negative side, that's called your reference angle, or theta ref. And in this case, it would be 60 degrees. It's what's missing between, if we went 120 degrees, and to go all the way to the other side of the x-axis would be 180. So we have an extra 60 there. That's going to be important later on. Radian measure. Okay, here's the definition of a radian. If you have some sort of circle that looks like this, and it's got a radius of r, there is an angle somewhere in there that subtends an arc. That's this part, the pi crust, that is the same length as the radius. So if you had 3 pieces of string that were all the same length, you could use 2 of them on the radius, and the last one you just lie along the circumference. Whatever angle that creates, that is called 1 radian. And the important equivalency is that pi radians is 180 degrees. We can have conversion factors to go back and forth, but you really should memorize some of the common angles. So if pi is 180, then pi divided by 2, well, that would be half of 180, or 90. Pi divided by 3, well, that would be 1/3 of 180, or 60. Pi over 4 would be 1/4 of 180, or 45. And pi over 6, that would be 30 degrees. The conversion factors are given below here, but I'm going to recommend that you use these as little as you can get away with. So to go to degrees, we just multiply by 180 over pi. To go to radians, it's by pi over 180. Over here, if I want to convert, here I'm in radians. I would want to go 2 degrees, so I could multiply by 180 over pi and then reduce. But what might be more effective is to think pi over 4 is 45. So this is 3 45s, or 135. That's a way to convert that's pretty quick. The next one, 7 pi over 6. That's 7 pi over 6s. Pi over 6s are 30 degrees. So this is 210. The next one, 3 pi over 2. Well, that's 3 pi over 2s, or 90 degrees. So that's 270. The last one, the 5.2, well, that's not one of our common angles. So we're going to need the conversion factor. So it would be times 180 over pi. And the reason we can multiply by 180 over pi is that that's really the number 1. 180 degrees and pi are the exact same thing. Let's check it out in a calculator. So we go 5.2 times 180 divided by pi. And that's about 298 degrees. Let's use the same logic in reverse. Down here we have 210 degrees. Is that a multiple of one of our special angles that we had up here? For sure. 210 degrees is not 3, is 7 30s. And one way we could say that is that it's 7 pi over 6s. That goes faster than using the conversion factor. Okay, 225, that's negative 5 45s. And a 45, oh, 45, if we check up here, is pi over 4. So we'd have negative 5 pi over 4. 120, you could think of it as 4 30s, but it's easiest as 2 60s. Okay, so that's 2 pi over 3s, or 2 pi over 3. Lastly, 73.9, we don't have a special angle that goes with that, so we'll just have to times by pi over 180 degrees. And you know which way to flip it because you want those degrees to divide out. Okay, let's go to the calculator. 73.9 times pi and divided by 180 is 1.29 radians. So those are the basics of radian measure and how we're going to convert between radians and degrees. Whenever we've got special angles or multiples of special angles, we do it with as little work as we can get away with. Arc length. Arc is just the crust on a circle. The length of an arc on a circle with a radius of r and a central angle of theta is given by this formula. And this is in radians for theta. Okay, so here's what it means. If you have some circle with a radius r and some central angle that we're calling theta, then the size of this, that's called the arc length, or the crust. And it's given by theta times r. Now you can do it in degrees as well, but the formula is more elegant when we do it in radians. Okay, let's put it to use. We want to find x. Well, over here, we know the central angle, and we know the radius is 8. The thing we're looking for is the arc length, which we're calling x. So let's just use this formula. Arc length is x in this case. Theta is 2.4. And the radius is 8. So it's just 2.4 times 8. Okay, let's go. Figure that out. 2.4. Bah. Try again here. Okay, and this time I hope that you've been able to figure this out on your own calculator. Okay, let's forget the calculator. 2.4 times 8 is going to give us 19.2. Okay, meters. The next one, I didn't put in an x here. We should have an x as the radius. That's going to be our unknown in this one. So in this case, the arc length is 29.2. The central angle is 4.3. And the radius is our unknown. Again, we're going to want to go to the calculator. So we'll have x is 29.2 divided by 4.3. And we just check it out on our calculator. I've got it behaving now. So 29.2 divided by 4.3 is 6.79. That's how big the radius of that circle must be. So the unknown could be the arc length, it could be the angle, or it could be the radius. Okay, moving along, we're taking a look at the unit circle. So the unit circle is really simple. It's a circle with a radius of 1, and it's centered on the origin. For all angles in standard position, here's what's special. Every point on the circle has these coordinates: cos theta, sine theta. The x value is cos, and the y value is sine theta. And some of the most useful points that come out of this are this one, this one, this one, and this one. This is telling us right here that the cos of 0, that's an angle of 0 right over here, cos of 0 must be 1 because it's the x value there. The sine of 0 is the y value there, is 0. Similarly, up here, this is telling us that the cos of pi over 2 is 0. And that the sine of pi over 2 is the y value at that point, is 1. Every point tells us cos and sine for that angle. X values are cos, y values are sine. Now, if we build up the unit circle, I can do it with my different special angles. So I could do 30 degrees or pi over 6. And I'd find that this coordinate right here would be root 3 over 2 and 1/2. And you can justify that either with special triangles or by knowing the trig table. Similarly, I could get 45 degrees or pi over 4. And the coordinates of that point would be root 2 over 2, root 2 over 2. Sometimes called 1 over root 2, 1 over root 2. Same values, just one has a rationalized denominator. Okay, for 60 degrees, we could do the same thing. 60 degrees or pi over 3. This point would be 1/2 root 3 over 2. And it's telling us that the cosine of 60 degrees, or pi over 3, is 1/2, and the sine of 60 degrees, or pi over 3, is root 3 over 2. From those, you could obviously figure out what's going on, say, at 120 degrees. It would be the same as 60, but in a different quadrant. So what's going to happen then? The x values are going to turn negative in that quadrant. And that gives rise to something that's really useful. Which ratio is positive in each quadrant? So because both the x and y values are positive in that first quadrant, both sine and cosine will be positive. And so will tangent. In the second quadrant, the x values turn negative. So that means cosine turns negative, and it also means tangent turns negative, because tangent's just going to be your y value divided by your x. So the only one that remains positive in the second quadrant is sine. In the third quadrant, both x and y are negative, so the only one that will be positive is tangent. And in the fourth quadrant, only your x's will be positive, so cosine will be positive, but sine will be negative, and cosine will be negative. At the end of this presentation and at the end of the downloadable notes, you'll find a full unit circle that's worked out. The unit circle is great for solving trig equations. Its only pitfall is that it can sometimes take a while for us to produce on an assessment. And if we botch up something, then the whole circle kind of gets messed up. Okay, 5, trig values. There are a lot of ways to learn or memorize the basic trig values for our special angles. You can do them with special triangles. You can do them with unit circle. You can do them with a hand trick. I've been a big proponent of using the table, but it really doesn't matter how you do it. One way or another, you need to know sine, cosine, and tangent for 30, 45, 60, and 90. And in radians, those would be 0, pi over 6, pi over 4, pi over 3, and pi over 2. We're going to find sine theta, cos theta, and tan theta. And it's super duper easy. Here's the trick. The sine row is root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. If you can count from 0 to 4, you can do this. Now some of these simplify. Root 0 over 2, well, that's just the number 0. Root 1 over 2, well, the square root of 1 is 1, so we call this a half. This one over here, root 2 over 2, it does not simplify, but it also has a non-rationalized form that looks like this, 1 over root 2. They mean the exact same thing. You check them in your calculator, they'll both give you the same value. Root 3 over 2, there's nothing we can do with, and root 4 over 2 would be 2 over 2, or 1. Okay? But this whole thing stemmed from root 0 through 4 all over 2. That's the sine row. If you can do that row, then the rest of it is super easy. The cosine row is just sine backward. Okay, so the sine row started at 0 and ended at 1. The cosine row is going to start at 1 and end at 0. Same values, backward. The last one, tangent, is just sine theta over cos theta. So this first one is pretty straightforward. 0 divided by 1. 0 divided by 1 is 0. 1/2 divided by root 3 turns out to be 1 over root 3. Or you can give it in its rationalized form, which is root 3 over 3. For 45 degrees, root 2 over 2 divided by root 2 over 2, well, anything divided by itself is just 1. 60 degrees, root 3 over 2 divided by 1/2 is root 3. And lastly, 1 divided by 0 is undefined. Now, whether you do it with the table, whether you do it with the hand trick, whether you do it with special triangles or the unit circle, you need to be able to find and use these values quickly. Now that we know them, we can use reference angles and ASTC, which was this business, tells us where each one is positive, to find the sine, cosine, or tangent of a multiple of any special angle. So let's do that. If we want to find these trig values, and we want to find them analytically, we don't want to use a calculator, I always want my table close at hand, and eventually it'll just be memorized and internalized. But here's what we do. We sketch the angle in standard position. Okay, so if I have sine 120, I'm going to sketch 120 degrees. There we go, no problem. We want to find the reference angle. That's the smallest angle that is made with the x-axis. And in this case, well, we had 120 degrees. What's missing to get us all the way around that line? We'd need another 60 degrees. That's the reference angle. Okay, so now we can go to the table. We're looking at sine of 60 degrees is root 3 over 2. The last piece of the puzzle is to use ASTC to correct for positive, negative. So over here we're in quadrant 2. Is sine positive or negative? We're in that S quadrant. That tells us that sine is positive here. I'm going to write it. You don't have to put that plus. But that is the answer. The sine of 120 is positive root 3 over 2. If we had been in, say, quadrant 3, then sine would have been negative. Let's try the next one. Cosine of 7 pi over 6. So let's think about this. 6 pi over 6 would be 180, or pi. And I go another pi over 6. This is the reference angle. And there's a nice little trick for when you're working in radians. Whatever this is, that will be your reference angle. Okay, it'll be pi over that number. So we went an extra pi over 6 compared to 180. Theta ref is pi over 6. Let's find it. Cosine of pi over 6 is root 3 over 2. Oh, what a coincidence. Same value. Now, let's check out the quadrant we're in. In quadrant 3, only tangent is positive. So that means that cosine in this quadrant is negative. Okay. If we had been in quadrant 1 or 4, then cosine would have been positive. Same thing happening over here, tan of 7 pi over 4. So 4 pi over 4 would look like this. Each one is another 45 degrees, so that's 5 pi over 4, 6 pi over 4, 7 pi over 4. This is going to be our theta ref here. It's 45 degrees, or pi over 4. And again, as soon as we see this, that it's something over 4, we'll know that theta ref is going to be pi over 4. Okay, so all we have to do is figure out what the tan of pi over 4 is. It's the number 1. Great. We fix it up for its sine, S-I-G-N. And we see that in quadrant 4, only cosine is positive. So tangent is negative. Okay, reciprocal trig ratios. So cosecant, secant, and cotangent have these definitions. They're just the reciprocals of sine, cosine, and tangent, respectively. So if I wanted to find the secant of 30 degrees, that's the same as 1 over the cosine of 30 degrees. And the cosine of 30 degrees is pretty easy to find. I draw 30 degrees. I use my table from the last page. Cosine of 30 degrees is root 3 over 2. Okay. So cos 30 is root 3 over 2. It's in quadrant 1, so it's going to be positive. So secant of 30 is just 1 over root 3 over 2. Now that hurts your brain to see that. But when we're doing 1 over that, basically what we're looking at is the reciprocal. So we're calling this 2 over root 3. If you were to do that division, it would look like this. 1 divided by root 3 over 2, which we know to divide fractions, we multiply and flip. So it gives us 2 over root 3, or that's sometimes written as 2 root 3 over 3. Okay. If we didn't want to do it with that step of figuring out what cos is, then we'd have to expand our table. And we'll look at that in just a second. Same idea here with cotangent of 3 pi over 4. That's the same as 1 over tan 3 pi over 4. And tan 3 pi over 4, well, here we go. There's 3 pi over 4. Theta ref would be pi over 4. Okay, and I've actually got a table down here, so I'll just scroll down. The tangent of pi over 4 is 1. And since we're in quadrant 2, it's going to be a negative 1. So tan of 3 pi over 4 equals negative 1. Cotangent of 3 pi over 4 is going to be 1 over negative 1. Or it's also coincidentally going to be negative 1. Okay. If you wanted to just know these values right off the top, then you could expand your table. And let's do that. So I think there's value in being able to get away without doing that. So let's go with another little trick. We've got our first 3 rows done. Cosecant is just 1 over sine. Okay? So I'll take this 0 and I'm going to flip it over. So right now that's 0 over 1. Flip it over, you get 1 over 0. 1 divided by 0 is undefined. Next one, 1/2. Flip it over, you get 2. 1 over root 2. Flip it over, and you'll get root 2. The next one, flip it over, you get 2 over root 3, which you can rationalize as 2 root 3 over 3. And the last one, 1 over 1, flip it over, and you still get 1. Okay, so we just took the reciprocal of everything from the sine line. You could do the same with cos and tangent, or you could use this little trick. Secant is just cosecant backward. Okay, so cosecant started with undefined, ended with 1. This one will start with 1, and it will end with undefined. 2 over root 3, or 2 root 3 over 3. Root 2, 2, and undefined. And cotangent, you can just do tan backward. So there are little tricks to being able to produce the table quickly. Tangent started at 0 and ended at undefined. Cotangent's going to start at undefined and end at 0. So if we did that, then this question up here with secant 30, it would have gone a little faster. We could have said, there's 30. Secant of 30 is 2 root 3 over 3. And since it's related to cosine, it's going to be positive in that quadrant. Answer is 2 root 3 over 3. So it does go a little bit faster if you have that expanded table. But we can work either way. Okay, before we get into the trig equations, one last piece that we have to take a look at is interval notation. And it's just an alternate way to show domain and range. So if you have square brackets, it indicates that the endpoints are included. If you have round brackets, it indicates that the endpoints are excluded. And plus or minus infinity is never included. So this first one here, let's say we had on a number line 0 to 2 pi. If I were to draw that interval, it would look like this. If I were to write it in interval notation, I would put my min, comma, max, and then I'd think, is that 0 included? Absolutely, it's got an equal sign. Is the 2 pi included? No, it doesn't have an equal sign. There's no equal sign there, therefore we're not going to include it. That's just the way of showing that interval using this different notation called interval notation. Okay, same thing here. X is greater than or equal to 3, so I could draw a number line to represent that. Over here there's 3. It's everything to the right of 3. So its minimum value is 3. Its maximum value is infinity. The 3 is included, and infinity is not included because we can never actually get there. So those are the basics before we actually hit the trig equations. All right, here we go with the real business of Chapter 4, solving trigonometric equations. We'll first look at these in the first revolution of angles in standard position. So let's get down to business. Here's the technique we'll use. We're going to find theta ref. We're going to use ASTC to sketch. So remember that looks like this. We're going to determine the angles in standard position and finally write our solution. Over here we've got cos x equals negative root 3 over 2. And we know that it's in the first revolution because it says from 0 to 360. That also tells us that we're dealing in degrees. So here's what I do. I look for a cosine of root 3 over 2 in my table. Or maybe with the hand trick, or maybe with the unit circle, depending on your preferred method. Either way, I figure this out. The reference angle is 30. Now you might say, but what about the negative? We'll deal with the negative next. That comes up when we pick our quadrants. So here we're talking about a negative cosine. Where is cosine negative? Well, we know it's positive in quadrants 1 and 4. It's going to be negative in quadrants 2 and 3. Okay, now let's sketch. What does that look like? Well, I'm going to make a reference angle. And remember, reference angle is always with the x-axis in quadrants 2 and 3. Now we just have to figure out what those angles are in standard position. So that first one would be like 180 degrees minus 30. Or 150. That second one, that would be 180 plus 30. Or 210. And those are our two solutions in the first revolution. You could throw them back into the equation, figure out what the cosine of 150 is, and it really would be negative root 3 over 2, or a decimal approximation of it. Let's try another one. Sine x equals root 3 over 2. So this is looking kind of familiar. Only now we're working in radians. So be careful of the domain. It will let you know whether you're in degrees or radians. You're in degrees if you see degree sign. If you don't, then you must be in radians. Okay, let's go ahead. Sine x is root 3 over 2. So sine needs to be root 3 over 2. That happens at 60 degrees, or, since we're working in radians, pi over 3. ASTC, sine is positive in this quadrant and this quadrant, right? Because this was a positive root 3 over 2. Now let's go ahead and sketch. So I need to sketch pi over 3 rather, which is about 60 degrees, or exactly 60 degrees, in quadrants 1 and 2. That first angle is easy to find. This is just pi over 3. This one takes a little more thought. It would be as if we went 180 degrees, or pi, and then subtracted pi over 3. So this is pi minus pi over 3. Think of that in a common denominator. It's 3 pi over 3 minus pi over 3. Hey, that's 2 pi over 3. And those are our two solutions in the first revolution. So when we have exact values, we look for them in the table. Here's one where we've got tan x equals negative 2. So I'll go for the same thing. I'll look on the tan line in my table, and I'll look for 2, and unfortunately it's not there. That's okay. All that means is that we're going to have to use the calculator to approximate our reference angle. And here's how it works. Still looking for theta ref. And I'm going to go inverse tangent. And just like before, we didn't care for the reference angle, whether it was negative or positive. We only looked at positive values. Here I'm going to go inverse tan of 2, of the absolute value of whatever this is. Okay, now I go to my calculator. What is the inverse tan of 2? Working in radians. So let's make sure we're in radian. Yep. Inverse tan of 2 is an angle of 1.11 roughly. Radians. We'll talk about what that looks like in just a second. Now think about ASTC. Tan is positive in quadrants 1 and 3. It's negative here and here, quadrants 2 and 4. Let's go ahead and sketch. So the question becomes, well, how big is 1.11? In a lot of ways, it doesn't matter. As long as you place it in the right quadrant, then everything's going to work out. You can think to yourself, well, 1.57 would be half of pi. So 1.57 is 90 degrees. So this is closer to 90 than it is to 0. So there's my angle of 1.11. And it occurs also in this quadrant. Okay, and what are we going to say? We need to find each of those angles in standard position. So the first one, I would think of that as pi minus 1.11. And I'd go to my calculator and find out what that is. 2.03. Okay, let's find the other one. I would think of this as a full revolution, but minus 1.11. And a full revolution is 2 pi. So 2 pi, 2 pi minus 1.11 gives us 5.17. Those are our two angles in radians that satisfy this equation. And they're approximate. They're not exact solutions, but they're very, very close. Lastly, secant x equals 5. So you'd like to say the same thing here. I'd like to go theta ref is the inverse secant of 5. Because even if you had the bigger table, it wouldn't have secant x equals 5 on it. The problem is our calculator does not have a secant button. So you need to convert to working in the primary trig ratios. And what we're going to do is flip both sides. You can do anything to an equation as long as you do it to both sides. So the reciprocal of secant would be cos. 1 over secant would be cosine. The reciprocal of 5 would be 1/5. Now we're ready to get to work. Theta ref, we don't have 1/5 anywhere in the table. So we'd have to go inverse cos of 1/5. And let's work that out. Inverse cos of 1 divided by 5 gives us 1.37. There's our reference angle. Secant and cosine are going to have the same signs, SIGN. So really, we can just work from this equation at this point. Cosine's positive, so we're going to be in quadrants 1 and 4. That's a pretty big angle, 1.37. But again, if you don't draw it as a big angle, your numbers will still work out. Okay, so the solutions, one of them is a dead giveaway. It's 1.37. The second one, you'd think of that as a full revolution minus 1.37. So 2 pi minus 1.37. Let's see what that gives us. 4.91. There's our other solution. The next thing we'll look at are general solutions. So in the last few questions, it always had this kind of domain. X is between 0 and 2 pi. But really, if we allowed ourselves to have an unrestricted domain, if you've got some question that has an answer of 60 degrees, you're also going to have an answer at the next revolution that ends up at 60. In other words, the next coterminal angle to 60. And you'll have one if we had happened to go backwards to 60. Or if we'd made a bunch of revolutions and gone to 60. So I could have all this. Still going to be a solution. So on an unrestricted domain, if one of the answers is 60, there's another solution at 60 plus another revolution, or 420. That red one backwards would have been negative 300. You'd have another one at 780, and so on, forever. Now, how do we show those? Well, we show them the same way that we would show coterminal angles, which is to say that all those angles take the form 60 plus 360 times n, where n has to be an integer. It can be a positive or negative number. So that means you can add on positive or negative multiples of 360. And those just mean revolutions in standard position. If you're doing it in radians, we'd be adding on 2 pi n. So we're going to solve as before. We're just going to add these extra little bits to represent all the infinite number of solutions that can exist if we have an unrestricted domain. So if we take a look here, cos x equals root 3 over 2, and it says solve it for all x, for every possible x value. It doesn't actually tell us whether it wants degrees or radians. So let's do both. If I were to do it in degrees, theta ref, I'm looking for a cosine of root 3 over 2. So theta ref is 30 degrees. ASTC, cosine is positive in quadrants 1 and 4. Make the little sketch. So 30 degrees and 30 degrees. Okay, so that gives us x equals 30. And that other one would be 360 minus 30, or 330. But each of those solutions recur every 360 degrees at all their coterminal angles. And I put n is an element of integers. Integers just means positive or negative whole numbers. So you can't have a portion of a revolution. You have to have a whole number, positive or negative multiple of that revolution. Okay, if we were to do it in radians, well, we'd do the same thing. Look for a cosine of root 3 over 2. Theta ref is pi over 6. Of course, we're still in the same quadrants because it's still the same question. Okay. There's pi over 6. Here's pi over 6. That first one is a gift. It's just pi over 6. The other one you'd have to think of as 2 pi minus pi over 6, which is the same as 12 over 6 pi minus pi over 6, or 11 pi over 6. But both of those solutions recur with every revolution. And a revolution in radians is 2 pi radians. Whether we're talking about this one over here or this over here, they're the same solution, just shown in different angle measurement systems. So they mean the exact same thing. Okay, solutions on a specific domain. So we need to find every angle that satisfies an equation, and we're given a specific domain. This actually happened when we did the first revolution, but it was kind of the most basic domain we could have, just the first revolution of your circle. So let's try this. Cos x equals a half for this domain, negative pi to 3 pi. I like to think of what this means. Negative pi means negative 180 degrees, or it's half a revolution backward. 3 pi, that's 540 degrees, or 1.5 revolutions forward. The actual equation is no harder than any of the other ones we've dealt with. Okay? And the sketch is going to help us find any extra solutions that might crop up. So let's just go with our basic approach here. Cos x is a half. Okay, so that means theta ref is pi over 3. ASTC, cos is positive in quadrants 1 and 4. Let's go ahead and sketch. So far, so good. So clearly there are going to be solutions at pi over 3 and whatever this one is. And it's really 2 pi, but minus pi over 3. Okay? And that would work out to be 5 pi over 3. Those are our solutions in the first revolution. Now, it also asks us to consider going backwards half a revolution. So if I start here and go backwards half a revolution, am I going to run into any solutions? Bang, right there, we run into one. What is that angle? If I've traveled backwards pi over 3, that's the angle, negative pi over 3. It also allows us to go beyond the first revolution forward. So let's see if I run into any solutions if I go beyond the first revolution. Here we go. I already got that one. Let's see. And I'm allowed to go another half revolution. Oh, we run into this solution again. So that one's just coterminal with pi over 3. It would be a full revolution plus another pi over 3. And if you convert to a common denominator and add those up, you'll get 7 pi over 3. Those are all the solutions on the specific domain. So these two we probably would have got either way. The other two we have to look for by going beyond that first revolution. The last thing we'll look at is combining quadratic and trig equations. So for quadratics, the plan is make one side 0, factor, and solve elementary equations. Over here, I have 4 cos squared x minus 1 from 0 to 2 pi. So first revolution, that's a little gift for us. If you're confused by the cos squared, just think of this as 4n squared minus 1. Does that factor? Absolutely. It's a difference of squares. So if that's true for the n's, then if we do it with cosine, here's what we'll get. 2 cos x plus 1 and 2 cos x minus 1 equals 0. Each of those gives us a little elementary equation. So either 2 cos x plus 1 equals 0, or 2 cos x minus 1 equals 0. And there is an alternate approach you could do here from the get-go, and we'll look at that in a minute. But first, let's just solve these elementary equations. Okay, so we factored, and we made each of those brackets equal to 0. I'm going to follow through on just this one over here. So it would be cos x equals negative 1/2. Okay, I'll do my regular stuff. I find theta ref. So where is cos 1/2? at that angle, which I know is pi over 3. Here, cosine's negative, so I'm talking about quadrants 2 and 3. We keep going down. If I were to sketch these, they would be pi over 3 and pi over 3. Okay, and that first one would be like pi minus pi over 3. It's a little less than 180, which would be 2 pi over 3. And the second one we run into would be more than 180. It would be pi plus pi over 3, which is 4 pi over 3. Okay, there are the solutions to one of these elementary equations. And they're definitely going to be solutions to the whole thing. But there may be more. So let's do the other side. 2 cos x minus 1 equals 0. That means 2 cos x equals 1, or cos x equals a half. Okay, theta ref. They happen to be the same in this case. They'll be pi over 3. But if it factored differently, then they wouldn't necessarily have to be the same. They'll always be the same if you have difference of squares, but on a trinomial, not necessarily. Okay, we've got a cosine in this case that's positive. So that puts us in quadrants 1 and 4. I'll sketch them. Pi over 3 and pi over 3. Okay, that means I have solutions of pi over 3. And this last one we'd think of as 2 pi minus pi over 3, which would be 5 pi over 3. Everything that's circled in red here, or squared in red, those are all solutions. So there are 4 solutions. And when you have quadratics, you know that that can mean more than one solution anyways. So your number of possible solutions can increase when you have quadratics. I just want to talk briefly about the very first step here in case you had an alternate approach. So if you saw this and you said, well, it's not a trinomial, so I'd prefer to do this. Make one side 1, isolate, and then square root both sides. That's fine. You can do that. But the thing you need to remember is that when you square root in an equation, and the square root of a quarter is a half, you need plus or minus. So it's still going to give you both of the elementary equations we had up below. They're up above, rather. Okay, so that's an alternate approach, and it's fine to do that. One last quadratic. 2 cos squared plus 3 cos x equals 2. So we know, since it's a quadratic, first of all, we know that it's a quadratic because it has a squared. So we need to make one side 0. Okay. If you find that hard to factor, then consider this. There it is without the cos x's. Now it's a long trinomial. You need either inspection, which is guess and test. You need decomposition, or you need a box method or magic x or some way to factor a long trinomial at this point. And going into that is beyond the scope of this video. Should be a prerequisite skill at this point. So we can try guess and test. Let's see. There we go. That'll work. That means that this over here factors, since it's the exact same values, to 2 cos x minus 1 and cos x plus 2. Each of those give an elementary equation. Okay. And this would be cos x plus 2. Now this one over here on the left we solved in the last one. Here we're solving it for all x, so I'll just go through it real fast. Cos x equals a half. Okay, that means theta ref is going to be pi over 3. That means we're talking about quadrants 1 and 4. That means the sketch looks like this. That the angles are pi over 3 and 5 pi over 3. And if we're solving for all x, each of these need a plus 2 pi n. Okay? Those are solutions. So I'll circle them in green. Now let's see what happens with the other elementary equation. I would rewrite this as cos x equals negative 2. I'd go to my table. I'd look for 2. No, it's not there for the cos. So I'd say, all right, that's okay. I'll just use the calculator. Inverse cos of 2. And I go to the calculator, and I type in inverse cos of 2, and it is not very happy. And your calculator won't be either. Mine says domain error. It just doesn't work. There's no such thing as a cosine value of negative 2. Okay, if you're talking about a triangle, a cosine of 2 would mean that you'd have an adjacent side that's bigger than the hypotenuse. That's not possible. No solution comes from this. Sine and cosine take values between negative 1 and 1 inclusive. Okay, so no solution from the right-hand side elementary equation, but all the stuff that we found in green on the left, that's still good. That brings us to the end of the Chapter 4 review. There is a review sheet along with complete work solutions that you can download, and there's a link to that in the video description below. And also, if you're looking for that unit circle, here it is, but that is in the notes as well, the PDF of the notes, which you can download. And again, that's in the video description below. Hope that this has been useful, and I'll see you soon.